All right, we're back with trigonometry. This is week 3, lesson 1, and we're going to be looking at complex numbers today. So I believe this is section 1.6 in the textbook. So complex numbers. And let's begin by looking at this quadratic equation, x squared plus 1 equals 0, okay? A simple quadratic equation. However, when we go to solve this equation, we have x squared is equal to minus 1. And so what we want to do is we want to take the square root of both sides of this equation. And if we do, we end up with an expression of the form x is equal to the square root of minus 1. And we can't take the square root of minus 1 in the real numbers. So there is no real number such that x squared is equal to negative 1. So what we're going to do is we're going to invent a new number, and this new number is called I. So we set I equal to the square root of minus 1. This is called an imaginary number. And it has the property that I squared is equal to negative 1. So it's not a real number because we know that a real number squared is going to be greater than or equal to 0. But this number has the property that when it's squared, it's equal to negative 1. So it's not a real number. It's a new number, and we call it I, and it's what we call an imaginary number. Now, I can take and I can multiply I by any real number. So I can, if I have a real number, let's call it B. So this is a real number. So real numbers, remember, real numbers are things like integers, fractions, the number pi, the number e, the number square root of 2, and so forth. Okay, so I have a real number b, and I can form the number b times I. So this is an imaginary number. And it has the property that when I square it, it's equal to b squared times I squared, which is equal to minus 1 times b squared, which is equal to minus b squared. So this is a non-positive real number. Okay, it's again an imaginary number because when I square it, I end up with a non-positive real number. Now, there are numbers called complex numbers. Complex numbers. And these are numbers of the following form. So these numbers have the form a plus b times I, where a and b are real numbers. Okay, so now let's look at this a little bit. A plus I times b. Okay, here I wrote b times I. I can write it b times I or I times b. It doesn't really matter. This number sitting here, this is a real number. And the number sitting over here, this is an imaginary number. Okay? So examples. So let's look at some examples of complex numbers. Well, let's say 2 plus I times 3. Okay, so this is a complex number. Here I have the real number 2, and here I have the imaginary number I times 3. I could look at 0 plus I times 2. This is actually equal to I times 2, which is the imaginary number. So imaginary numbers are complex numbers. And then I could look at something like this. I could look at, let's say, 3 plus I times 0. Now, I times 0 is equal to 0, so this is just equal to 3, which is a real number. And so we have that real numbers are also complex numbers. Okay. Now, what can we do with complex numbers? Well, one thing that we can do with complex numbers is we can add them together. So suppose I have two complex numbers, let's say a plus I times b, and c plus I times d. So these are two complex numbers, and I want to add them together. So I want to take a plus I times b, and I want to add it to c plus I times d. Well, this is equal to the complex number a plus c plus I times b plus d. So what I'm doing is I'm taking the real part of these two complex numbers, the a and the c, these are both real numbers, and I'm adding them together to get a real number here, a plus c. And then I'm taking the two imaginary numbers, I times b and I times d, and I'm adding those together, and I get the imaginary number I times b plus d. Okay, here I'm using the distributive law to pull out the I, which is a common factor on I times b and I times d. So let's take a look at how this works. So I have 2 plus 3 times I, and again I can write this I times 3 or 3 times I, plus 5 plus 6I. Okay, so this is equal to, I'm going to sum these two complex numbers together. So what I'm going to do is I'm going to sum the two real numbers together, the 2 and the 5. And when I do, I get 7 plus, and then I'm going to take and I'm going to add the two imaginary numbers together, 3I plus 6I, and maybe I'll write it here, 3I plus 6I, and this is equal to 7 plus, well, 3I plus 6I is 9I. Okay, let's try that again. Let's try one more. Suppose I have minus 3 plus 2I plus 1/4 plus, what should I make this? Let's make it 1/2 I. Okay. So this is going to equal. So I am summing two complex numbers together. This is going to equal minus 3 plus 1/4 plus 2I plus 1/2 I. And this is equal to, well, this is equal to minus 12 divided by 4 plus 1 over 4. So this is minus 11 over 4 plus, and here this is going to be 4 over 2i plus 1 over 2i. That's going to give me 5 over 2i. So that's my sum, right? Let me mention this. If I have a complex number, so complex number that I'm going to call z, and this is equal to a plus I times b. So again, a and b are real numbers. Okay. So here I have, this is a complex number, and I'm calling this complex number, I'm calling it z. Then I'm going to define the real part of the complex number z. I'm going to set this equal to RE of z. So RE here stands for real part. So this is the real part of z, and the real part of z is a. Okay? And then we also have the imaginary part of z, which is denoted by IM. So the IM stands for imaginary part of z. So I'm looking for the imaginary part of the complex number z. Now, you might think that's going to be I times b. It isn't. It's just going to be b. Okay? So both the real part and the imaginary part of a complex number are actually real numbers. So again, here we're looking at the real part of z. Excuse me. And the real part of z is just going to be the real number a. And then the imaginary part of z, this is where it gets a little bit confusing, because you would think, oh, that's going to be I times b. That's the imaginary part. But what we're going to do is instead we're just going to write the imaginary part of z is just equal to the factor b, which is the factor on I. So as an example, we might have something like 5 minus 2i. Okay, so this is my complex number z. And I want to look at the real part of z. This is equal to 5. And I want to look at the imaginary part of z. And this is equal to negative 2. Okay, let's try another one. I have minus 1 plus 7i. So this is my complex number z. And I'm looking at the real part of z. This is equal to minus 1. And the imaginary part of z is equal to not 7i, just 7. Okay? How about if I had this? Z is equal to 8i. Well, 8i is equal to 0 plus 8i. So the real part of z is equal to 0, and the imaginary part of z is equal to 8. Okay. All right. With complex numbers, we can also multiply them together. So we can multiply two complex numbers. And let me show you how that's done. Suppose I have the complex number z is equal to a plus ib, and I have another complex number which I'm going to call w, and this is equal to c plus I times d. Then I can form the product, z times w. This is equal to a plus I times b times c plus I times d. Now, the distributive law applies. We always want the distributive law to hold, and in this case, I can write this as a plus I times b times c plus a plus I times b times I times d. Okay, so what did we do? We looked at this factor here times c, that gave us this first term, and then we looked at a plus I times b times I times d, and that gave us the second term here. Okay, now this works out as follows. So I can apply the distributive law again. So when I do, I have a times c plus I times b times c. Okay, so these two terms come from this first term here. And now we're going to do the same thing over here. So this is going to be plus a times I times d plus I times b times I times d. Okay? Now, multiplication is commutative. So I can write a times I times d as I times a times d. And then over here, what do I have? I have I times b times I times d. So I'm going to rearrange this. I'm going to take I times I, which is I squared, times b times d. And this in turn is equal to, so I'm going to write this again, a times c plus I times bc plus I times a times d minus, because I squared is equal to minus 1, b times d. And now let's collect the terms. So these two terms sitting here, this one and this one, these are imaginary numbers, right? Because it's a real number times the imaginary number I. Whereas this term here and this term here, these are real numbers. So I'm going to sum those together. So I'm going to write this as a times c minus b times d plus, and then I have I times bc plus I times ad. And now what I can do, I have I sitting here and here. This is a common factor to these two terms, so I can pull it out. I can redistribute, and when I do, I get the following. And that is how you multiply two complex numbers together. Okay? Notice this is the real part. And this is the imaginary part. Okay, so let's look at an example. So suppose I have z is equal to 2 plus 3i, and I have w is equal to 5 minus 4i. So let's multiply these two complex numbers together. Z times w. This is going to be 2 plus 3i times 5 minus 4i. And this is equal to, well, it's going to be 2 times 5, which is 10, plus 3i times 5, which is 15i. Plus, then I have 2 times negative 4i, so this is minus 8i, plus 3i times negative 4i. So what do I have? 3i times negative 4i. So I have I times I, that gives me negative 1. And then I have 3 times negative 4, and that gives me negative 12. So I have negative 12 times negative 1, and that gives me plus 12. So then I'm going to collect common terms. I'm going to look at the sum of the two real terms. This is going to be 22. And then the sum of the two complex, or the two imaginary terms, and this is going to give me 7i. So that's my product. All right. So try to do some of the suggested problems and work out a few of the multiplication type problems. Now, there's more, a lot more to complex numbers. One thing is, if I have a complex number z, this is equal to a plus I times b. We're going to see that this is an important concept, but for now, I'm just going to define it. Then we could say the conjugate of z is equal to a minus I times b. So if I have the complex number z equal to 2 plus 3i, then the conjugate of z is equal to 2 minus 3i. And this is usually denoted by conj of z. So conjugate of z is equal to 2 minus 3i in this case. If I have w is equal to minus 1 minus 5i, then the conjugate of w is equal to minus 1 plus 5i. So I just changed the sign here. Okay. And then we have something called the modulus of a complex number z equal to a plus ib. This is denoted by, it's like putting the absolute value sign around a number. This is the modulus of the complex number z, and this is equal to the square root of a squared plus b squared. Okay? And we'll see how this comes into play when we look at the geometric interpretation of complex numbers. For now, I want to look at this though. Suppose I have z is equal to a plus I times b, and I look at the conjugate of z. This is equal to a minus I times b. So let's look at the product. So I'm going to take z times the conjugate of z. All right? And this is equal to a plus I times b times a minus I times b, which is equal to, well, it's going to be a squared plus I times b times a, right? And then it's going to be plus minus I times b times a, right? So it's this term here times this term over here. And then I have minus b times I have I times b times minus I times b. So I times I is equal to negative 1 times the negative 1 from the minus sign times b squared. So this is just going to be plus b squared. And now look, this is equal to a squared plus b squared. These two terms cancel out. So when I take a complex number z and I multiply it by its conjugate, I get a real number. Okay? And in fact, the real number that I get is the number that appears underneath the radical sign here in the definition of the modulus of the complex number. Let me also mention, many times, often, the conjugate of a complex number is denoted a little bit differently. So right now, if we have z is equal to a plus I times b, I said that the conjugate of z is equal to a minus I times b. A lot of times this is written as z with a bar above it. So this z with a bar denotes the conjugate of z. So this is the conjugate of z, and this is equal to a minus I times b in this case. And so we have the following. We have z times the conjugate of z, which often is just written as z times z bar. This is equal to a squared plus b squared. Okay? Now, there's another operation that we need to talk about, and that's division. So I have a plus I times b divided by c plus I times d. And I want to figure out, so this is going to be a complex number divided by a complex number. And what I'd like to do is I'd like to figure out what is the real part of this number and what's the imaginary part of this number. So I'm going to have to perform some sort of operation in order to make this denominator a real number. And what I'm going to do is I'm going to multiply this by 1, but it's going to be 1 in the following form. It's going to be c minus I times d divided by c minus I times d. So all I'm doing is I'm taking the conjugate of the denominator, and I'm dividing it by itself. So this is the number 1. This is just equal to 1. And so when I form this ratio and I multiply it by my complex number over here, a plus ib divided by c plus id, I'm not changing anything. This is still equal to a plus ib divided by c plus id. Okay. Now let's do the multiplication here. So when I multiply these two complex numbers together, what I'm going to do is I'm going to multiply the denominators together, and I'm going to multiply the numerators together. So let's write this as a plus ib times c minus id divided by c plus id times c minus id, which is its conjugate. Now, what do we know? We know that when we take a complex number and multiply it by its conjugate, this is going to equal, it's going to equal the real part squared plus the imaginary part squared. So this is c squared plus d squared, and this is being divided into a plus ib times c minus id. Now let's expand. Let's expand this numerator. So we get a times c plus I times b times c minus I times d times a plus I times b times minus I times d, all divided by c squared plus d squared. And this in turn is equal to Well, it's going to be A times C, and then let's look at this term here. Here I have I times B times minus 1 times I times D. Well, we know that I times I is equal to minus 1, times the minus 1 from the minus sign, that gives me 1, times BD. So this is plus B times D. And then plus, and then here I have I times BC minus I times DA. The I happens to be common to these two terms, so I can pull it out in front and write this is I times BC minus DA, all divided by C squared plus D squared. Okay, so if I'm looking for the real part of A plus IB divided by C plus ID, what is that going to be in this case? It's going to be the real part of this complex number sitting here. It's going to be the real part of this, and that's AC plus BD divided by C squared plus D squared. And the imaginary part of A plus IB divided by C plus ID, this is equal to BC minus DA, all divided by C squared plus D squared. Okay, let's work out an example of this. So we have, let's say 2 plus 3i divided by, let's make it 3 plus 4i. Okay, so what I want to do, so what I want to do is I want to find the real part of, and I'm going to call this z, and the imaginary part of z. So that's what I want to do. So what we're going to do is we're going to take 2 plus 3i divided by 3 plus 4i, and I'm going to multiply it by the conjugate of the denominator divided by the conjugate of the denominator. So it's going to be 3 minus 4i divided by 3 minus 4i. So I'm not changing anything. I'm just multiplying my complex number z by 1. And this is equal to, well, this is going to be 2 plus 3i times 3 minus 4i divided by 3 plus 4i times 3 minus 4i. And this in turn is equal to, okay, so now we have to do the multiplication. Well, we know when we multiply a complex number by its conjugate, it's just going to be the real part squared plus the imaginary part squared. So this is just going to be 9 plus 16. And then I have to do the multiplication up here in the numerator. So this is going to be 2 times 3, so I get 6, plus 3i times 3, and that's going to be 9i. And then I have 2 times minus 4i, so this is going to be minus 8i, plus 3i times minus 4i. So that's going to be I times I is negative 1, times the negative 1 due to the minus sign, so that's 1, and then times 3 times 4, and that gives me 12. So this is plus 12. And now I'll collect terms. So this is 18 plus I divided by 25. So the real part of z is equal to 18 divided by 25, and the imaginary part of z is equal to 1 divided by 25. Okay. All right, so look at some of the suggested problems. Suggested problems. These are listed in the syllabus. And we'll pick it up from here next time. Bye.